Welcome to the new era of video creation with Bayozi8. This is our new series on AI teaching natural language processing. Today, we will discuss the named entity recognition. Here are the contents. Named entity recognition, NER, is a core task in natural language processing, NLP, that involves identifying and classifying entities in text into predefined categories such as people, organizations, locations, dates, and more. For example, in the sentence, Apple was founded by Steve Jobs in Cupertino, NER would recognize Apple as an organization, Steve Jobs as a person, and Cupertino as a location. NER is a critical component in many information extraction tasks. It helps machines extract meaningful information from unstructured data, making it easier to process and understand text. For instance, in search engines, NER helps in identifying relevant entities for user queries. In question answering systems, recognizing named entities can help direct the system to the right information. NER is pivotal for several high-impact NLP tasks. Information extraction. NER helps automatically extract key facts from large volumes of text, such as extracting company names, product names, and event dates from news articles or social media posts. Search engines. NER enables search engines to better understand and rank results based on entities. For example, recognizing Apple as a company and Steve Jobs as a person helps refine search results. Question answering, QA. NER is crucial in QA systems. Identifying entities like people or locations can guide the system in finding relevant answers from a knowledge base. Sentiment analysis. By identifying named entities, NER allows sentiment analysis models to determine the sentiment of specific entities, such as gauging the sentiment towards a product or a celebrity. The main goal of NER is to identify entities in text and classify them into predefined categories. The most common categories include persons, PR. This category includes individual people, groups, or fictional characters, such as Albert Einstein or the Beatles. Organizations, ORG. This category identifies names of companies, institutions, government bodies, and other organizations, such as Google, United Nations, or Tesla. Locations, LOC. This includes names of countries, cities, landmarks, and geographical features like New York, Amazon River, or Mount Everest. Dates, times, date, time. Identifying dates, times, and temporal expressions such as March 15, 2025, or next Tuesday. Miscellaneous, IMESC. This category includes other named entities like product names, events, and percentages. For example, iPhone 12 or Olympics 2024. NER faces several challenges that can complicate the identification and classification of named entities. Ambiguity. A word might refer to different entities depending on the context. For example, Apple can refer to the tech company or the fruit. The model needs contextual clues to disambiguate between these meanings. Contextual variability. Entities might be expressed differently in various contexts. For instance, New York might be written as NYC in other contexts. The system must recognize these variations and understand that they refer to the same entity. Named entity variations. Named entities can appear in different formats or spellings. For example, John Smith may be written as John S. Smith or Dr. John Smith in other instances. These variations need to be recognized as referring to the same entity. Multilingual issues. In multilingual contexts, NER becomes even more challenging. Some languages may not use spaces between words, or names might be presented in different scripts. For example, the name Dongjing in Chinese is the same as Tokyo in English, but a NER system must recognize this equivalence across languages. NER systems can be categorized based on their approach. Rule-based systems. These systems use a set of manually defined rules to identify named entities. For example, if a word starts with a capital letter and is followed by another capitalized word, the system might tag it as a possible name. While this approach works well for some applications, it is limited by its inability to generalize to new, unseen data. Statistical methods. These methods rely on machine learning techniques such as hidden Markov models, HMMs, and conditional random fields, CRFs. These systems are trained on labeled datasets and learn the statistical relationships between words and their associated entity types. They can handle more variability in the data compared to rule-based systems. Deep learning methods. More recently, deep learning techniques, especially recurrent neural networks, RNNs, LSTMs, and transformers, e.g., BERT GPT, have shown impressive results for NER tasks. These models can learn complex patterns and dependencies in text, making them more robust and adaptable to new data. At its core, NER is a sequence labeling task, where each word in a sentence is assigned a label that represents its role as a named entity. The task is to tag each word based on its position and category. For example, in the sentence, Steve Jobs founded Apple in Cupertino, the model would label Steve Jobs as BPER, beginning of a person entity, Apple as B.org, beginning of an organization entity, and Cupertino as B.lock, beginning of a location. In sequence labeling, the labels are typically assigned in the BIO format. B marks the beginning of an entity. I marks tokens inside an entity. O marks tokens that are outside any named entity, e.g., founded in the example. NER systems are typically evaluated based on their ability to correctly label these tokens, and the performance is measured using metrics like precision, recall, and F1 score. Evaluating NER systems involves several key metrics. Precision measures how many of the named entities identified by the model are correct. For example, if the system tags Steve Jobs as a person, but also incorrectly tags founded as a person, the precision would decrease. Recall measures how many of the true named entities present in the text the system successfully identifies. High recall means the system identifies most entities, but it may also result in more false positives. F1 score. The F1 score is the harmonic mean of precision and recall, and it provides a balanced evaluation metric. It's especially useful when dealing with imbalanced data, e.g., many non-entity words in fewer entities. Accuracy. This is simply the percentage of correctly labeled entities out of the total entities. It is a general metric, but it might not always reflect the nuances of performance in real-world applications. In recent years, deep learning techniques have significantly improved NER performance. Recurrent neural networks, RNNs, particularly long short-term memory, LSTM networks, are well suited for NER because they can capture dependencies across words in a sentence. For example, LSTMs can remember previous words in the sequence to help identify entities even when they are separated by other words. The introduction of transformer-based models, such as BERT, has revolutionized NER. These models are pre-trained on massive amounts of text data and then fine-tuned for specific tasks like NER. Fine-tuning involves adjusting the weights of a pre-trained model to better fit a particular NER dataset. BERT and other transformer models have set new benchmarks for performance in NER tasks as they capture bidirectional context and are capable of handling complex linguistic features. NER in multilingual settings presents unique challenges. Different languages have varying syntax and structures, which can impact the ability of a NER system to correctly classify entities. For example, while English uses spaces between words, languages like Chinese or Japanese do not, requiring different tokenization and parsing techniques. Cross-lingual models, such as XLMR, cross-lingual model, and MBERT, multilingual BERT, are pre-trained on multiple languages and can be fine-tuned for NER in any of those languages. These models allow for zero-shot learning, where they can recognize entities in languages they haven't explicitly seen during training. Training data for multilingual NER needs to be diverse, covering a range of entities and contexts in multiple languages. This makes it challenging to build high-performing systems for all languages. NER has widespread applications across various fields. Information retrieval. Search engines use NER to identify and rank results based on named entities. For example, when you search for Google CEO, NER helps identify entities related to Google and its CEO. Document categorization and summarization. By extracting named entities, systems can categorize documents or generate summaries that focus on key people, places, or events. Healthcare. NER is useful for extracting medical entities like diseases, medications, and procedures from clinical texts, improving patient care by enabling better data mining. Legal. In the legal field, NER is used to identify case names, laws, and court decisions, helping professionals navigate large volumes of legal documents. There are many popular tools and libraries available for implementing NER. Spacey, a fast and efficient NLP library in Python that provides pre-trained models for NER across many languages. It is highly customizable and is commonly used in production systems. Stanford NER, a Java-based tool developed by Stanford NLP Group. It's one of the older and more widely used systems for NER, featuring models for multiple languages. Hugging Face Transformers, a collection of pre-trained models, including BERT, Roberta, and Distilbert, which can be fine-tuned for NER tasks. Hugging Face provides an easy-to-use Python API for integrating these models. Allen NLP, a library built on PyTorch, which includes several models for NER, making it a good choice for research and experimentation with deep learning approaches in NLP. Looking ahead, several advancements are likely to shape the future of NER. Improved handling of ambiguity. While current NER models have made significant strides, ambiguity remains an issue. Future systems might leverage better context-based understanding and world knowledge to handle ambiguous entities more effectively. Cross-lingual and multilingual NR. As global data grows, the ability to perform NER across multiple languages will become even more important. Multilingual models like MBERT and XLMR will continue to evolve, allowing NER systems to scale efficiently across languages. Integration with knowledge graphs. Integrating NER with knowledge graphs could enhance entity recognition by allowing systems to access structured, domain-specific information about entities. Zero-shot learning. The ability to perform NER on unseen entities or in languages with limited training data through zero-shot learning techniques will become increasingly important for flexible, real-time NER. To summarize, named entity recognition, NER, is a vital task in NLP that helps identify and classify entities such as people, organizations, locations, and dates. Over the years, NER has evolved from simple rule-based systems to sophisticated deep learning models, allowing for more accurate and context-aware entity extraction. Despite challenges such as ambiguity, multilingualism, and diverse entity formats, NER remains a core tool in a wide range of applications, including information retrieval, question answering, and healthcare. As deep learning and multilingual models improve, the future of NER looks promising, with further advancements in accuracy and domain adaptability.